Hi there. Thank you everybody for having me here. Thank you, fabulous, and thank you all for coming to the talk. So focus a little bit about what Pixelligent has been, where we are today, and where we're going in the future. Pixelligent at its core, we are a nanocrystal company. So we create primarily higher refractive nanocrystals on a mass scale, and then we can incorporate those in different resin systems in order to create both nano-optics and micro-optics using wafer-level manufacturing. Mostly work with consumer electronic applications, work with a little bit of automotive as well, and incorporating our materials into micro-lens arrays. Core markets are definitely Silicon Valley, optics and sensors, as well as display. The optics and sensors is where we kind of fit into some of the automotive work. Our company's based in Baltimore, Maryland, on the east coast of the U.S. Everything that we do is under one roof today, including our sales and administrative staff, our R&D department, our product management group, and our manufacturing. See on the left a few of the reactors where we grow the nanocrystals. We have the capacity to make up to 10 tons of zirconia a year, 15 metric tons of titania a year, as well as have spare capacity to create an additional 80 metric tons should the material is for it. A little bit about the history of Pixelligent, where we've been, where we are today, and where we're going. Started off with our company founders, including our current Chief Technology Officer, Dr. Phil Williams, and they developed a way to manufacture sub-20 nanometer metal oxide nanocrystals and then stabilize them using organic ligands as capping agents for surface treatment. Pixelligent 2.0 was taking that technology that they developed and scaling it up to the ton scale with 3 specific metal oxides, including hafnia, zirconia, and titania. And zirconia and titania is where we focus a lot of our products today. Today, we incorporate our zirconia and titania in several different resin systems. And then going on in the future, we plan to use some artificial intelligence tools that we have at our disposal that we've been plugging data into for the last several years to expand to 20 different metal oxides that we've identified as being applicable with our manufacturing process. This slide kind of shows how we make our materials and then where they go into the different products. So you saw the reactors a few slides ago. We grow their nanocrystals in a bottom approach that allows us to maintain the size of the nanocrystals very precisely, as well as make sure that they have good surfaces on the nanocrystals themselves. And that tight size control helps us to create haze-free films and micro-nano objects. Once we have our nanocrystals grown to the desired size, we put them into a capping process. In that capping process, we attach organic ligands to the metal oxide nanocrystals in order to stabilize them and prevent aggregation. We work really hard to create very small nanocrystals, and we want to keep them that way and not have them bind together to create boulders. Instead of making sure that they're pebbles in our different solutions. Once we have our capped nanocrystals, there's 3 different ways we distribute our material. One is as a dispersion, where it's just our nanocrystal in solvent. That's a starting point for other people to formulate around. We have a second starting point, which is our base formulations, where our nanocrystals are dispersed into monomer resin, like benzyl acrylate, for example, which acts as a different starting point for other people to formulate. And the most interesting piece that we have are our final formulations, which are fully UV curable formulations that are designed to be put down onto wafers, either via spin coat or inkjet, and then they can be imprinted by nano-imprint lithography methods to create the different structures, like the one on the right there, which is a small section of a nanograin. A little bit more about the stars of our show being the nanocrystals. We have zirconia, titania, and also our Pixcore nanocrystal down there. Going in reverse order, our Pixcore nanocrystal has a titania core and a zirconia shell around the outside of it. That enables us to try to get the best of both worlds from the materials. Titania has a slightly higher refractive index compared with zirconia, but it also is more UV catalytic compared with zirconia. So the zirconia shell helps to mitigate a lot of the UV catalytic effects that we see from titanium. There is a small sacrifice to the refractive index that we get, but that is more than made up for the reliability improvement. Also have our large titanium and our zirconia on the slide. You can see the SEM images on the left shows that we get good dispersion without much aggregation thanks to our capping agents. And then we also have a dynamic light scattering, or DLS curve. This curve shows the monodisperse size of the nanocrystals that we're very proud of. We actually report the D49 number, or the 99.99th percentile largest nanocrystal in a given batch. We have a maximum specification of 70 nanometers for our large titanium and Pixcore nanocrystals, and 30 nanometers for our zirconia. We try not to hide any of the any of the size of nanocrystals by reporting that figure instead of showing either just the midpoint or the D75 number. And again, that type size control helps us to control some of the optical dispersion, optical scattering, and create haze-free films. Here's a cartoon showing the capping agents coming off from the nanocrystal. So we've got typically two different kinds of capping agents on a given nanocrystal. And by controlling the ratio of those capping agents, we can get the nanocrystals to have some different properties, including adding functionality to the ends of the ligands to help it bind into the organic resin system. All right, and now shifting away from the nanocrystals, going more into the formulations that are used to create the different optical components. The two water bottles shown here are Pixnel ST2, which is a solvent-containing titanium formulation that can make a 1.9 refractive index film. And we also have Pixelligent SFC5, which is one of our inkjet coatable solvent-free zirconia formulations. We've got several different formulations here, and getting a little more details about them. Some of our solvent-containing formulations that are used to make nanogratings with very small residual layers and film thicknesses that range anywhere from 100 nanometers to about a micron, including our zirconia, our Pixcore nanocrystals, as well as our titanium nanocrystals. Pixnel ST2, as I mentioned, can have several different dilutions, as all of our solvent-containing formulations have, which control the film thickness, and also we can get very thin residual layers all the way down to 20 to 30 nanometers. Also pictured, we've got Pixnel ST6, which is a very stable formulation that we use to make high aspect features, and Pixnel ST5, which is our 2.0 RF formulation. Here's some cutaway images showing that we can get the nanocrystals very well dispersed within a given optical feature. So we don't have a delta or gradient refractive index that's continuous all the way through. So we metallized some of the nanocrystals, so you can see them at the top of the structure, all the way down to the bottom, and then highlight that the residual layer is only 2 to 3 nanocrystals high. Big slanted gratings, still with a very thin residual layer, and a few other options here. I want to take this time to give a shout out to some of the partners that have helped us develop some of our formulations, including SUSE Microtech, EV Group, Optool, NILT, and Morphotonics, that have taken some of our material and made structures using their equipment. EV Group helped us publish a white paper last year showing some of the differences between our latest resin utilizing our core shell material and comparing that against a filler-free material, which is a 1.5 RI. So the results wind up being very similar, including with slanted grading, high aspect ratio, and also place grading formulations. So don't let anybody fool you that filler material isn't quite as imprintable as filler-free material. So that's about where Pixelligent's been. Where we're going today is working on the processability of our materials as well as the environmental reliability testing. So this slide shows some of the development that we've had going from Pixnel ST2 to Pixnel ST13. We're able to have a soft bake process temperature range that can be significantly higher to make sure that we're driving off all of the solvent out of the formulation prior to imprinting. And working on Pixnel ST14, 15, 16, and so on today, but those are still under some development today. Getting away from nano optics and talking about some of our micro-optic materials, that's where our solvent-free material comes in. It still contains a lot of our or everything we do contains our nanocrystals we develop, but our solvent-free materials design to make thicker films and taller features. Some of our material is utilized to make glasses-free 3D displays, as well as different refractive optic elements for dot projectors, diffusers, and then different sensors that come in. On the right, you can see some of our formulations that have made nanopillars for meta lenses, as well as some of the different micro lens arrays there in the middle. These are some of our solvent-free materials, including utilizing our zirconia, pixel, and titanium nanocrystals again. Unlike our solvent-containing materials, they have a little bit higher viscosities to them. And the trade-off for Pixelligent is that the more nanocrystal we load into a resin, the higher the RI, but also the higher the viscosity. Once we get to about 70 to 75% weight loading of our nanocrystals, we start to get to a pretty high viscosity. That means imprinting and creating wafer-level optics and nano gratings a little bit more challenging. So it's one of the things that our product development team is working on today, is working with different resin systems to lower the viscosity of some of our solvent-free formulations. You can see an example here of hemispherical lenses that were imprinted using silicone stamp, also compatible with PDMS stamps. And we're looking for new applications and new partners to help us develop our micro-optical formulations further. I mentioned where we're under development today is our process window and also our reliability. In addition to new resin systems, taking our titanium and zirconia further, we continue to develop with our Pixelligent technology. That's about 1.5 to 2 years old at this point. This is a graph showing that for 500 hours of QSEN testing, the core shell material has a DE star or delta E star, showing how yellow the material gets. It's about 4 times better than what our titanium material has in the same test. So a couple slides ago, we showed some of our standard materials for both solvent-containing and our solvent-free materials. But just like a DJ can tune the knobs, or a sound engineer can tune the knobs and make a recording sound a little bit different, we have lots of knobs that we can turn to customize our different formulations to make them just right for specific sets of requirements. So if the standard formulations don't work, then we can utilize some custom formulations with our in-house product development team.